Bismillahirrahmanirrahim. Welcome to the lecture on mass storage. So in this lecture we are going to discuss about the disk storage device. So in this lecture the topics what we are going to discuss are the mechanics of disks, disk scheduling algorithm, and the concept of formatting and booting, RAID, redundant array of independent disks, then swap space management technique. Already we have discussed this in the previous lecture, this concept, the mechanics of disk, the internal structure of a hard disk. So the disk consists of platters, and you can see here three platters, 1, 2 and 3. Okay, this is platter 1, platter 2 and platter 3, and each platter has two surfaces, top and bottom surface, and the platters are mounted on a spindle. This is the rod on which this platters are mounted. It is called a spindle, and each surface of a platter has a read write head. You can see this read write head. This read write head for the top surface, and also for the bottom surface there is read write head, and these read write heads are connected to the arm assembly. So basically the platters, they rotate around the spindle, and the read write, okay, once again the surface of each platter is divided into tracks. So there can be n number of tracks in each and every surface of a platter. So you can see here one track. So similarly there can be n number of tracks. Each track is divided into smallest storage unit of smallest unit of storage, that is called sector. So each track is divided into sector. So this is the track. Please understand, there can be many tracks in each and every surface of the platter. Similarly, tracks, okay, of tracks in different platters of the same radius, okay, makes a cylinder. So let's say this radius is 3, some measurement, this radius, the track of this radius and the track of this the radius of these 3 tracks are same, so they constitute a cylinder. So tracks of the same radius make cylinder. For example, let's say here we have 200 tracks in this surface, then we can understand that there are 200 cylinders on the disk. Okay, so 200 tracks here in each surface, that means we can understand there are 200 cylinders on the disk. Okay, so this is the basic internal structure of a hard disk. The platter, as I said before, the platter would be rotating like this, okay, and the read write head would be moving from one track to another track. So from track 1 to track 2, track 2 to track n, like that it would be keep moving from one track to another. And to read specific data in a specific area of the disk, okay, the read write head would be placed on the specific track, and until when the sector available in that track comes below the read write head, the reading or writing operation takes place. So please understand, the read write head would be moving from one track to another, okay, and the platter would be rotating, and to read specific data in a specific area of the disk, okay, the specific sector has to come below the read write head. So this is how the disk operation happens. So when the data is stored and to be accessed from the disk, okay, the address is made up of various components like drive number, okay. So like maybe we have let us just assume there are more than one drive in a system, so each drive has a specific number, so that is a drive number. Then as I said before, cylinder, okay. So let's say this is track 1, this is track 1 and this track 1, and all these tracks have the same radius, so they make, let us say, okay, they constitute a cylinder. Let's say this is cylinder number 1. So like that, there would be many cylinders in a disk. So to access a specific data, the address is very important, okay. So the address is made up of these components: drive number, cylinder number, and surface number. You know what is a surface? There are surface like top surface and bottom surface, okay. Then sector number. So address basically is made up of drive number, cylinder number, surface number, and sector number, okay. So these are the basic information about the disk. Hello. So now let us discuss about the very important concept, that is disk scheduling algorithm. So just imagine that some input or output request is coming to the disk. The applications they want to access the disk for reading or writing purpose. So we can refer that as IO, input or output. So when many applications they try to, or when many processes, when they try to when they send some request to the hard disk at the same time, these requests has to be scheduled in a specific order, okay, because they have to be processed, okay, one after another, not concurrently, okay. So we need some disk scheduling algorithm. This disk scheduling algorithm, like the algorithm what we discussed in the chapter 4, CPU scheduling algorithm. So in chapter 4, the CPU scheduling algorithm would schedule the processes which wants to access the CPU. Here in this case, disk scheduling algorithm, okay, the processes they want to do some reading or writing operation, so they send some requests. These requests has to be ordered by some disk scheduling algorithms. So now we are going to discuss some disk scheduling algorithms such as FCFS, first come first serve, then SSTF, shortest seek time first, and then scan, then cscan and clook. These are some of the disk scheduling algorithm which we are going to discuss in this lecture. FCFS scheduling algorithm, according to the FCFS scheduling algorithm, the process which come the request which come first would be processed first, okay. Let's say these are the pending IO requests, okay. So let's say some processes they want to do read or write operation with the disk, so they are sending the request. So these numbers actually refer to the track or cylinder number, track or cylinder number. Okay, let's say this is 98, 183. So some process wants to read some data in a specific sector in the track number 98. Okay, or I can say in the cylinder 98, and another process wants to do some read or write operation in the cylinder number 183. Okay, for simplicity just try to keep this as track number. Okay, and another maybe same process or some other process wants to do some read or write operation in the track number 37. So in the track number, so the read write head, what it will happen to the read write head, it will go to the track number 37 and it would wait until the appropriate head comes below the read write, until the corresponding sector comes below the read write head. Okay, so this is track number is very important. Okay, now let us say the current head position is 53. The position of the current head position is 53. Okay, so from 53 the head actually, this head has to move from one track to another track like this. It has to move from one track to another like that, from track 0 to track 1, track 2, track 3, track 4, track n, like that it will move. Okay, so now let us see how it happens in the FCFS disk scheduling algorithm. So now current head position is 53. Okay, so now these are the pending requests. The first request is to the track number 98. Okay, so the head will move from track 53 to 98. Why it is going to 98? Because this is the first request. Whichever request is coming first, that will be processed first. So from track number 53 the head is moving to track number 98. Okay, now actually what I am showing you is that I am showing how this disk scheduling algorithm will make the head move. Okay, so when the head is moving from one place to another, how it will happen according to the FCFS disk scheduling algorithm. Okay, and from that we can compare the efficiency of different algorithms. So when the head movement is more, when the head is moving more distance to perform the read or write operation, if the head movement is more, then the amount of time taken to do access a specific sector and do the read or write operation, that we can call it as a seek time, that will be more. Okay, so basically if the head movement is proportional, sorry, the seek time is proportional to the head movement. If the head movement is more, then the seek time is more, that is the time taken to do the reading or writing operation in the hard disk. Okay, we can, okay, that also increases seek time. Okay, so the current head position is 53. From 53 it moves to 98. Then from 98 it moves to the next request track number, that is 183. From 183 it moves to 37, and from 37 it moves to 122. From 122 it moves to 14, and from 14 it moves to 124, and from 124 it moves to 65 and 67. So this is the total head movement under the FCFS disk scheduling algorithm. So totally how many tracks it has moved, or we can say how many cylinders it has moved. It has moved around 640 cylinders. 640 cylinders to perform the reading or writing operation in these tracks or cylinders. Okay, so this is how the FCFS disk scheduling algorithm works. Now let us do a simple workout. Okay, just read the question. Suppose the head of moving head disk with 200 tracks. So there are 200 cylinders or 200 tracks in the disk. In each surface there are 200 tracks. Okay, and the tracks are numbered from 0 to 199. The current head position is 100, and before, earlier the read write head was in the track number 105, but now the current head position is 100. This is very important for you. Now these are the pending requests. Okay, for simplicity let us reduce this. Okay, these are the pending requests. Now you have to calculate the total head movement, how many tracks or how many cylinders the head has moved according to the FCFS disk scheduling algorithm. Okay, so let us say these are the input. Okay, so let's say this is track 0 because total number of tracks in each surface is 200 tracks. Okay, from 0 to 199. Okay, okay, so now basically the current head position is 100. So the current head position is 100. Now there is a request to the track number 25. So the read write head will move from 100 to track number 25. So from current head position is 100, from 100 it will move to track number 25. Okay, then it will move to track number 45. Then from 45 it will move to 102. So this is how the track is read write head is moving. So from 100 it is moving to 25, then it is coming to 45, and now it is 102. So what is the total head movement? How much distance it has moved? So you have to do the calculation. So let's do this. Equal to the current head position is 100. So from 100 it is moving to 25. Then from 25 it is moving to 45, and then from 45 it is moving to 102. Okay, so now, so how much distance it has moved? 100 minus 25 is 75, plus, okay, 20 plus 57. Okay, so plus 57, so totally 152 cylinders. Okay, so this is the total head movement according to the FCFS algorithm. Suppose let me increase one more value, let's say 10. Okay, so let's say 10. So let's see what's happening. Then the head will move from here to here. Okay, from here to here. So here plus 102 minus 10, okay, plus plus how much? $92. Okay, so $244. So this is how the FCFS disk scheduling algorithm works. Whichever request is coming first, that request would be processed first. Okay, so if any problem is given to you, okay, let's see one more problem. We'll discuss some more problems like this. Just a minute. This. So like this, you can work out many sample problems. Okay, your teacher would be distributing these tutorials to you. Okay, just try to solve these tutorials. Okay, so like this the problem would be given. Okay, read the question. These are the pending requests. You have to find how many tracks, then you have to find what is the current track. So the current track number is 143. Before that it was in 125. This is not important. You have to start from here. What is the currently serving a request? Current track number is 143. So as far as the FCFS is concerned, from 143 the head will move to 86. From 86 it will move to 147. From 147 it will move to 91. From 91 it will move to 177. From 177 it will move to 94. From 94 it will move to 150. From 150 it will move to 102. From 102 it will move to 175. 175 it will move to 130. So like that you can calculate the total head movement like this. Okay, and even you need not draw the diagram like this. You need not draw the diagram like this. Try to find the total head movement. Okay, so from the head movement we will know whether you have understood this disk scheduling algorithm or not. Okay, now let's move to the second disk scheduling algorithm, that is SSTF. The advantages of the FCFS disk scheduling algorithm: it's very simple, and there is no starvation. Okay, so the process, the request, in a specific order, the whichever request is coming first, that would be processed first. However, the amount of distance the head moves is more as far as the FCFS is concerned. So when you compare this the head movement with other disk scheduling algorithm, you will know. Okay, when you compare you will know which is efficient one. The next one is called shortest seek time first. So according to this disk scheduling algorithm, we have to choose the request which is nearest to the current head position, shortest, which has the shortest distance from the current head position. Let's work out this here. Now the current head position is 53. From 53, which request in the queue, pending queue, which has the shortest distance? Okay, so from 53 the shortest distance is 65. Yes or no? 65 minus 53 is 12, whereas 53 minus 37 is like 13, 16. Okay, so the 65 is the request at track number 65 has the shortest distance to the current head position. So please understand, according to this algorithm, the head will move to the head position which has the shortest distance from the current head position. Okay, so the current head position is 53. From 53, okay, it will search each and every request and it will find which is the nearest one. The nearest one is 65, so it will move to 65. Now the head is in 65. From 65, again it will check each and every request and find which request is nearest to the current head position of 65. Which one? 67. So from 65 it will move to 67. Okay. Now from again it will check the pending request. Okay. Which request has shortest distance from the current head position of 67. The shortest distance from the current head position is 37 to the request 37, this request. Okay, so from 67 it will move to 37. From 37, which is the shortest one? 14. So from 37 it will move to 14. Okay, from 14 the next nearest one is 98. Okay, from 98 the next nearest one is 122, and from 122 the next nearest position is 124, and finally it will move to position 183. So this is how the SSTF disk scheduling algorithm works. But this disk scheduling algorithm has a disadvantage. Just assume the current head position is 53. Okay, and these are the pending request. Just imagine the the request keep coming, okay, from the system. Okay, the queue keeps updating, new request keeps coming to the queue. So the queue is always getting updated, new requests are coming, and the new requests continuously flowing into the queue. Just imagine like that. Here you can see there are 3, 4, 5, 6, 7, 8 requests are there. So in the real time it won't be like this. The request would be keep coming to the queue. Okay, it won't be a fixed static one like this. Okay, the request would be keep coming. Suppose now the current head position is 53 and many requests are coming to the queue, and whichever request is near to the 53, that request will be processed, and whichever request which is far away, distant from the current head position of 53, that would be delayed for longer duration. So any request which is very far away from the current head position will suffer from the problem of starvation. Why? Because their processing will take long time. The request, okay, will be processed later. Whichever request is coming near to the current head position, that would be processed first. So any request which is far away from the current request, okay, that would be delayed. So this problem is called starvation problem. This SSTF disk scheduling algorithm suffers from the problem of starvation. Okay. Now let's do the total head movement. Okay, the current head position is 53. From 53 it is moving to 65. From 65 it is moving to 67. So that calculation is given here, and when you do the calculation you will find 236. So the total head movement is 236 cylinders. Okay, so when you compare this SSTF of 236 and FCFS of 640, you can clearly understand that SSTF is the efficient algorithm. The total head movement is less. You understand? So the seek time is less. I already told you the seek time is proportional to the head movement. If the head movement is more, the seek time also more. So if seek time is more, the amount of time taken to do the read or write operation in the hard disk could be more. You understand? So you can see the total head movement as far as the SSTF is just 236, whereas in the case of FCFS is 640. and we can come to a conclusion that SSTF produces lesser seek time, whereas FCFS the seek time is more. Okay. However, the problem with the SSTF is it suffers from the problem of starvation. Okay. So let's work out a simple problem here. Same problem. Let's solve it using SSTF. Excuse me. So the current head position is 100. Okay. So 100. From 100, you have to analyze this queue and find which request is near to the current head position of 102. So from here 100, it will move to 102. Just compare with FCFS. FCFS means from 100 it will move to 25. Why it is moving to 25 in FCFS? Because 25 is the first request. But now we are discussing about SSTF. As far as the SSTF is concerned, the head will move to the request which is nearest to the current head position. So 102 is the nearest. Okay, 102 is the nearest to the current head position of 100. Next, from 102, which is the nearest request? Of course 45. So it will move to from 102, it will move to 45. Okay, then from 45 it will move to 25. Then from 25 it will move to 10. For demonstration purpose, students, I have put these values in the first row. Clear to you? For demonstration purpose, is it clear to you? So whatever values given in the queue, that you can put it here. Then it is easy for you to draw the directions from one track to another. Okay. So let's calculate the total head movement. So the current head position is 100. From 100 it is moving to 102. From 102 it is moving to 45. From 45 it is moving to 25, and from 25 it is moving to 10. So I am not going to complete this calculation. You can complete the calculation. You understand? So 100 minus 2 plus 57 plus 20 plus 15. So you can put whatever resultant values you are getting. You understand, students? Clear? So this is how SSTF disk scheduling algorithm works. The main problem with this algorithm is starvation. Okay, if the incoming request is near to the current head position, then that request would be processed, whereas the request which is coming to the track which is very far away from the current head position, that request would be delayed. Okay, so this problem we can say as starvation. So this is what I want to say about SSTF. Now let's go to scan algorithm next. Next disk scheduling algorithm is scan disk scheduling algorithm. So this according to this disk scheduling algorithm, the head will start from the head position and it will move towards it will move in one direction until it reaches the last track or last cylinder, then it will come back in the opposite direction. So, when it is moving in one direction, whichever request is in that direction, that request would be processed. For example, as far as this scan is concerned, in this particular problem, the head is current head position is 53. It is moving, the head is moving towards the track 0. Okay, so you can ask one question, why it is moving in this track 0, why not towards 199? I will answer that question. This you can find from the question itself. When you read the question, you will understand correctly in which direction the head is moving first. Clear? Now let us assume the head is moving first in the left direction first. It is moving towards the track 0. So, when it is moving towards the track 0, okay, just you check the queue, how many requests are in this direction. Okay, that track number 37 is falling in this direction and track number 14 also falling in this direction. Is it clear to you? So, when the head is moving, no, okay, it will find there is a request for the track number or cylinder number 37, so that would be processed. Then it would find there is a request at track or cylinder number 14, so that also would be processed. Then after that you can verify that there is no more request in this direction. However, the head would simply move towards the track 0, then it will change its direction. It will move in the opposite direction. So, when it is moving in the opposite direction, please understand, already the request at track number 37 and track 14 already it has been processed, Okay. So, the next request in the opposite direction is track 65, then 67, then 98, then 122, then 124, then 183. So, 183 is the last request in this direction. So, we need not go to the 199. Why? Because this is the last track. You understand? So, now this is how the the scheduling algorithm works. The head will move in one direction, whichever request is coming in that direction, that would be processed, and the head would touch the last track and then it would turn in the opposite direction. When it is moving in the opposite direction, or whichever request is lying there, that would be processed. Clear to you? Okay. So, according to this disk scheduling algorithm, the total head movement is 208 cylinders. So, when you compare with previous one, SSTF 208 and this one FCFS 640, this is sorry 236, this SSTF. I think there is a mistake here, just you do the calculation and find what is the correct result. Okay. So, the scan disk scheduling algorithm is 208. So, from this we can understand that this one is very efficient one. Okay. Now, let us do the calculation, let us work out a tutorial problem. Okay, these are the pending requests, 4 requests. Now, we have to read the question properly. How many tracks are there? 200 tracks, or we can say cylinder or tracks. Okay. There is a request, currently the head is stationed in the track 100, that is current head position is 100. Previously it was in 105, but the current head position is 100. So what you understand from this? The head is moving from 105 to 100, that is, it is moving from right to left direction. It is moving in the left direction. You understand? From 105 it is moving to 100. You understand? So what do you understand? It is moving in the left direction. Suppose here 105 and here 100. So from 100 it moved to 105. The current head position is 105. So what do you understand? From 100 it moved to 105. Let's say this is 105. From 100 it moved to 105. So the head is moving in the right direction. So from these two values, students, you can understand the direction in which the head is moving initially. Okay, so so the previous head position was 105 and the current head position is 100. Okay, so that is from 105 it is moving to 100. It has moved to 100. That means it is moving in the left direction. So the current head position is this. This is the current head position, and you have understood that it is moving in the left direction. So when it is moving in the left direction, please understand what are the pending requests in the left direction, which are before 100 track 100, 45, 25 and 10. Okay, so from 100 it would be moving to 45, then it would be moving to 25, then it would be moving to 10, okay. So after that there is no pending request in this direction. However, as far as the scan is concerned, okay, it will move until the track 0. Okay, you can say it is waste movement from track 10 to 0. Yeah, but however our algorithm works in this way. It will touch the track 0 and then it will change its direction. From here it will go to track 102. Okay, so it is moving in the left direction first, then it is turning, it touches the last track and then it is moving in the opposite direction. When it is moving in the opposite direction, there is one pending request in track number 102 that is processed. Suppose let us say there is another request here. Okay, then what happens? This would be moving from here to here. So if you ask, can whether to extend this movement to the last track, no need, because you don't have any other request, pending request. Is it clear to you? So this is how the scan disk scheduling algorithm works. Just a minute. Let's do the calculation now. The current head position is 100. From 100 it is moving to 45. From 45 it is moving to track number 25. From 25 it is moving to 10. So after that, even though there is no more request in that direction, however the head will move towards the last track, that is track number 0. From 0 it will go to track number 102, from 102 it will move to 150. So the initial head movement is 100, from 100 it is going to 45, from 45 it is moving to 25, 25 it is moving to 10, then 10 to 0, 0 to 102, from 102 it is moving to 150. If you do this calculation, you will find what is the total head movement. Okay. So let's do this. 55 plus 20 plus 15 plus 10 plus 48. So you can find what is the total value. Okay, you will come to know what is the total head movement. 55, 20, 15, 10, 102, 48. Okay. So this is how the scan disk scheduling algorithm works. So advantage is there is no starvation, it is fair to all the requests. However, there is a disadvantage. The middle region of the hard disk, okay, it has the request which lies in the middle region of the hard disk are favored more than the request which comes at the end of the disk. Okay, so requests for the middle of the disk are advantaged over those at the ends. So this is the disadvantage of the scan algorithm. So that problem can be sorted out using C-scan. We will discuss the C-scan next. Next disk scheduling algorithm is C-scan disk scheduling algorithm. It is same like scan disk scheduling algorithm, but when the head moves to the one end, when the head moves to the last track, it goes straight to the other end without servicing any request. That is, C-scan algorithm will process the request only in one direction. That just keep this in your mind. The scan, actually you see, it is moving from right to left, it is processing all the requests in the middle on the way, then it is moving from left to right, it is processing all the requests on the way. So it is processing the request in both the direction, scan algorithm, but C-scan will process the request in only one direction. So the current head position is 53. Okay, it is moving in this direction. While it is moving in this direction, it is processing all the requests on the way. That is 65, 67, 98, 122, 124, then 183. Then it is moving to the last track. Same like scan, but now you see while it changes its direction, okay, in the reverse direction, it is not processing any request on the way. There are two pending requests. In 37 track there is a request, and also there is a request in track number 14. There are two requests, but these two requests are not processed while the read write head is moving, returning in its reverse direction. Then again it from the last track it goes back to the first track, then it starts the changes the direction, then it processes all the requests on the way. So you can see it is processing all the requests in only one direction, not in two direction, whereas scan algorithm process the request in both the direction. That's a big difference between scan and cscan, because in the scan, no, the middle region, this region of the hard disk has more advantage. Any request which comes in the middle region would be processed quickly as far as the scan scheduling algorithm is concerned. To overcome that drawback, the cscan, what it does, it will process the request only in one direction. Okay, let's work out this tutorial problem now. These are the pending requests. Okay, so now the current head position is 100. Previously the head was in track number 105. So from 105 it has moved to 100. That means it is moving from right to left, From 105 it has moved to 100. So from this you can understand the in which direction the head is moving. So track number, the current head position is 100. From 100 it has moved to track number 45. From 45 it has moved to track number 25. Then from 25 it has moved to track number 10. Then after that, even though there is no more request pending in that direction, but still the read write head will reach the first track, the ending position, and then it changes the direction. While it changes the while it has changed the direction, it is not processing any request. There are two requests pending here in 102 and 150, but in the reverse direction these requests are not processed, because the rule says cscan has to process the request in only one direction. So the head is moving from right to left. So when the head is moving from right to left, all the requests would be processed. When it's moving from left to right, the request will not be processed. Okay, so again the head will from this end it will go to the other end, then it changes the direction in the in this different direction. The request which is lying on the way would be processed. There is a request in the track number 150 that is processed. Then there is a request in track number 102, it is processed. So this is the difference between the scan and cscan. Let's work out the total head movement. The current head position is track 100 minus 45 plus, from 45 it is moving to 25. Then from 25 it's moving to 10. Then from 10 it's moving to 0. Then from 0 it's moving to 199. Then from 199 it's moving to 150. Then from 150 it's moving to 102. So this is the total head movement. You can solve this and you can do the calculation and find what is the total head movement. So let me verify again. It's moving from 100 to 45, then 45 to 25, then from 25 to 10, from 10 it's moving to 0. Okay, you can ask, okay, this head movement is best. Of course, as far as this algorithm is concerned, this is how it works, but still this head movement could have been avoided. This problem would be would be solved in the next algorithm which we are going to discuss. Then from 0 track it is moving to track 199. Then from 199 it's coming to 150. Then from 150 it's moving to 102. So this is how cscan algorithm functions. There is nothing significant to discuss about these things. Let's next we will move on to uh, C-look disk scheduling algorithm. So the next algorithm is C-look scheduling algorithm. It's same like scan, C-scan, but there's a difference between the C-look and C-scan, except that rather than going to the ends of the disk, we only go as far as the furthest request in each direction. So here the head is moving in this direction. The last request in this direction is in the track number 183. Just compare the C scan and scan. After this track, it is moving to the last track. From 183 it is going to 192, even though it is not necessary, but this algorithm works in this way. Clear? So this head movement is really waste of time. So this is what is avoided in the C-look algorithm. This is C-scan. Okay, when you avoid this, okay, you just cut this from 183. Let us make the head move from 183. Let us make the head move to 14. From 183, let's make the head move to 14. Then this algorithm will become C-look. In C-scan, this is C-scan algorithm. Okay, it's okay, already. I have explained enough. So here, if this is the last request in the C-look, okay, the head will not move to the last track. Okay, if there is no request, then it will not move to the last track. Rather, it will change its direction, and in the opposite direction, whichever request is at the end, okay, from that request the processing will start. Okay, not from 37 but from 14. Okay, so this is in this direction. Okay, it will change the direction. It will go to the other end. In the other end, whichever request is first, in the other end, whichever request is first, from that request the processing will start. Now you check from 183, the head is moving to 14, then it is coming to 37. Okay, just compare with this is C scan and this one is C look. Now let's work out this this example. Let's change to C look. So what changes we have to make here? So here, let's say in this direction, the track number 10 is the last request. After that, the head is moving to the end track. So this is not needed as far as the C look is concerned. Now from track 10, it will go to the other end. In the other end, okay, which request is starting is the first request. The other end, track number 150 is the first request. Okay, so in this direction, okay, from the last request, the head will move to the other end. In the other end, whichever request is first, it will start from that. So from it will process the 150, then it will come to 102. So this is how the C look actually works. So let's make some changes here. Okay, so this is not needed as far as the C look is concerned. So this is not necessary. So basically what happens, from 10 it moves to 150, and from 150 it goes to 102. So this is how the C-look algorithm works. So the total head movement, in fact, as far as the C-look is concerned, it is far less compared with other disk scheduling algorithms. So please understand, let me reiterate, when the head movement is more, the seek time will be more. If you want to analyze any disk scheduling algorithm, if you want to compare the disk scheduling algorithm, then you can compare based on the concept of seek time. So seek time is connected to the head movement. If the head movement is more, seek time is more. Then next one is fairness. Fairness means whether any algorithm brings starvation problem. So one algorithm can bring starvation problem, that is called shortest seek time. Okay, some request processing would be delayed. If the request is far away from the current head position, that request processing would be delayed. So this algorithm is susceptible to the starvation problem. So please you have to understand, when you want to evaluate the algorithm, when you want to analyze and judge which is good algorithm, okay, then we can do based on these two criteria. One is seek time, another one is fairness. Fairness is nothing but whether the algorithm has starvation or not. Okay, if there is no starvation, that means the algorithm is a fair algorithm. Okay, so far we have discussed the FCFS disk scheduling algorithm. Then we have discussed the shortest seek time first scheduling algorithm. In short, we can call this as SSTF. So be careful, this algorithm is susceptible to the starvation problem. Then we went to scan scheduling algorithm. Okay, then the scan scheduling algorithm, the problem is the middle region of the hard disk is advantaged. Any request is coming to the middle region, that would be processed immediately or quickly. That's a drawback. So that problem is addressed in the next one, that is C-scan. Okay, however, there is a unwanted head movement from here. The last head track to the head is moving to the first track, and while it is moving, no request is processed. That problem is addressed in the C-look algorithm. So this is what I want to say about the disk scheduling algorithm. Next, let's discuss the concept of formatting. Basically, formatting can be classified into low level and logical formatting, high level formatting. The low level formatting is done while the disk is manufactured in the factory. It is a process of creating the sector. Already we have discussed this. The disk surface has tracks and sectors. Okay, smallest unit of storage. The size is usually 512 bytes. 512 bytes. So when the disk is manufactured, the sectors are created. So this is the structure of a sector. Each and every sector has a number, okay, header number, and then this is the area where the data is stored, around 512 bytes, and this, the end part, tail part, is called error correcting code, is to check the integrity of the data stored. So this is the structure of a sector. Okay, header, it's a unique number, each and every sector has a unique number. This is the data where, okay, for example, if the data you are storing a file, its size is 1000 bytes, okay, then it would be stored in 2 sectors, okay, because 1000 bytes means you cannot store the entire data in single sector, because single sector can hold only 512 bytes. Is it clear to you? So like that, the to store files, many sectors would be used. Okay, so low level formatting is done at the factory while the sectors are created. Then of course we can do the partitioning. We have the hard disk, we can logically divide it into many partitions like C, D, E, and also we can change the file system while we okay, we can change the file system NTFS, XT, ext3, ext4. Okay, so this is called logical formatting. The next concept is called bad blocks. So the sectors basically can become corrupt, can be damaged, can get damaged. So such sectors are called bad sectors or bad blocks. Sectors on a disk sometimes become defective. Okay, such sectors are called defective sectors. So when sectors are corrupted, damaged, the the hard disk might fail and we might lose the data. So always on our part we have to check when the disk becomes old, we have to check once in a while whether any bad sectors exist or not. So let us see how we can check the bad sectors in the Linux and Windows operating system. So the corrupted sectors in a disk is called bad sector. We need a strategy for preventing these bad sectors. So basically the two strategies adopted are simple and sophisticated. Under the simple, a program is used to scan the bad blocks. So as far as the Linux operating system is concerned, let us see how to find bad sectors. So you have to execute this command sudo fdisk -l. So it would show you the list of devices available, okay, partitions or devices available. Okay, then let's say we want to check the bad sector in this particular device. Then there is a program in the Linux that's called bad blocks. Just invoke that program, bad blocks -s space, then the device which you want to check the bad blocks. Okay, so when you give, it would scan and let you know whether any bad sectors available in the system or not. If there are any bad sectors available, then it would be the operating system would maintain a list of bad sectors. So that list would be updated whenever a new bad sector is found in the disk. Then the operating system would update its list, so that next time when some data has to be saved in the disk, then the operating system would take the necessary precautions that the data are not stored in the bad sector. Okay, so this is how we can scan the bad sector in the Linux. In the Windows is concerned, you can open the command prompt and you can execute this command check disk chkdsk check disk. Then the partition which you want to check for the bad sector, like C colon or D colon. Let's say for example we want to check the bad sector, check disk space D partition D colon space /r. Okay, so it would check for the bad sectors. If there are any bad sectors are found, then the system would update its list of bad sectors, so that next time the data would not be saved on to the bad sectors. So this is a strategy which is used by the system to overcome the bad sectors. So bad sectors are not good. If any bad sector comes in the disk, then that means the system is eventually going to fail. So it is better to move the data to to another storage device. Okay, so basically I want I like the students to know what is a bad sector. Okay, so what are the strategies we can adopt as a user? Like we can just I showed we can invoke some programs. Okay, like in Linux bad blocks -s space the name of the device, or in Linux or in Windows check disk space the partition colon space /r. So we can invoke this programs periodically to check for bad sectors, and the system would have a list of bad sectors, and that whenever a new bad sector is found, that would be updated, so that the data would not be stored in the bad sector next time. Okay, so the operating system basically what it does is, like it would allocate a spare sector, a good sector actually, for the place of bad sector. It's just a replacement. Okay, it is a backup plan, we can say. And the spare sector basically it has to be near the bad sector, so that it doesn't affect the disk scheduling algorithm. So this is not in our hand actually. We cannot do, as a user we cannot do anything, but my advice to you is that please try to know what is the bad sector and what are the strategies to handle the bad sector practically, using Linux command and Windows command. You should be knowing practically, but for theoretical purpose just understand the concept, what's a bad sector and what are the strategies to handle the bad sector. The next concept what we are going to discuss is redundant array of independent disk. So let's imagine a scenario. We have some data in the disk, and if the just now we discussed about the bad sector, the bad, if the sector is corrupted, we might lose the data in the disk. So so what is the strategy to recover the data in case if the data in some disk is damaged, okay, is lost? So that strategy is called RAID strategy, redundant array of independent disk. Okay, there are many RAID levels are there. Just let me play a video so that you understand what are the different RAID levels available. So RAID is a technique to prevent the data loss. RAID abbreviation is redundant array of independent disks. So as far as the RAID concept is concerned, the data are stored on multiple disks. So in the event, if case of data is lost in one disk, the data can be recovered from another disk. That is the basic idea behind the concept of RAID. So now there are many RAID techniques are there: RAID 0, RAID 1, RAID 5, RAID 10. So RAID 0, what happens is that the data are spread across multiple disks, like two disks here. So this, let's say this is the full data. So part of data, let's say A is copied into the disk, this disk 1, and the B part is copied to the disk 2. So like that, but we cannot say RAID 0 as a fault tolerant technique. Suppose if this disk is lost, is damaged, then we cannot retrieve the entire data. So this is a shortcoming of RAID 0. So you can ask, if RAID 0 is not fault tolerant, what is the use of RAID 0? Since we are using two disks in place of one disk, the amount of time taken to do the read or write operation would be less. So it improves the performance. So basically, in order to improve the speed, improve the performance, multiple disks can be used, but this is not fault tolerant. We cannot prevent the data loss using the RAID 0 technique. So in the RAID 1 technique, multiple disk, let's say two disks, have the same data. So whatever data in the disk 1, that is copied onto the disk 2 also. So in the event of any damage happens to disk 1, the data can be retrieved from the disk 2. So it is a fault tolerant and it can prevent the data loss. So you can see this disk is damaged, but still no problem, the data can be retrieved from the disk 1. So this is called RAID 1 technique, and the name for the RAID 1 is mirroring and duplexing. Okay, so exact, each and every disk has the exact copy of the data. This is called RAID 1 technique. So next technique what we are going to discuss is called RAID 5. or that I can explain using with a simple example. So let's say the disk 1 has this data and the disk 2 has this data, and let's say this is disk 3. There are 3 disks, disk 1, disk 2, and let's say this is disk 3. Disk 3. So whatever data in the disk 1 and disk 2, we do XOR operation. So you know what is the XOR operation. So when we do the XOR operations, we get this output. Okay. Okay, so if we do the XOR and we get the output, and this is called parity block. So the parity block is stored on the third disk. Okay, so let's say now if let's say the disk 2 is damaged. Now this particular disk is damaged. Okay, now we want to retrieve the data, the disk 2 data. So how to retrieve the disk 2 data in case if it is damaged? So we can retrieve like this: disk 2 data is equal to parity block XOR disk 1. Okay, so let's do this. This is the disk 2, sorry, this is the parity data XOR, this is the disk 1 data. What we get is the output what we get is nothing but disk 2 data. So for each block of students, for each block of data, the data first would be spread across multiple disks. Okay, and for a parity block would be created in one of the disk. So if any one block is damaged or corrupted, then that block can be retrieved using the other blocks in the other disk and the parity block. Using this you can retrieve the damaged block in any disk. So such technique is called blocked interleaved parity, or we can say RAID 5. So a parity bit for the group of subblocks is returned to the special parity block. If one of the block is lost, it can be recovered from the other subblocks plus the parity block. So I have explained that using this example. Clear to you, students? So what's a RAID? RAID is the organization of multiple disks. Multiple disks are used, and these disks are high performance disks. Okay, to back up the data, to prevent the data loss. So this is a RAID is a fault tolerant technique. So basically the data will be copied into multiple blocks, multiple disks. So if one disk is damaged, the data can be retrieved from other disk. So there are many types of RAID techniques which you have seen in the video which I showed you before, like RAID 0, RAID 1, RAID 5 and RAID 10. Now we are primarily discussing about the RAID 2 technique, okay, and the RAID 5 technique. So in the RAID 2 technique, also we can call it as mirroring. Each disk holds all the data. So whatever data you have in the disk 0, same set of data you will have in the disk 1. Whatever data in the disk 0, that will be in the disk 1 also. The other one is like creating a parity block, and for each set of blocks, some set of blocks, a parity block is calculated, and if any block is damaged, then that data can be retrieved using sub blocks plus the parity block that I have explained using this example. Is it clear? So you must know the mirroring technique and blocked interleaved technique. You must know. Also you should know this example. Clear? Okay, so this is RAID technique. Let's continue with the next concept. Now let's see how the booting process works in a system. So how the operating system is loaded, when the system is powered on, how the operating system is loaded. So that we are going to discuss. So operating system basically loaded into the main memory using a program called Bootstrap Loader, and let us see the steps involved in the booting process. So now you can see
several key pieces of forensic information and as a forensic examiner to control the boot process to use forensic.
Now you can see when the power is switched on, okay, the power is switched on, the power goes to the system. So this is the read only memory. You know, there is a device in the motherboard, ROM, read only memory. The read only memory, there is a BIOS, basic input output service. Okay, so in that there is a instruction that is called post power on self test. So when the system is powered on, please understand, the control goes to the this post instructions are executed. These post instructions are in the in the read only memory. You understand? So what this post will do, when the system is powered on, the post instructions are executed. So what this post will do, it will just check, it will initialize the registers, it will check the devices whether they are connected properly or not. Like it will check the, you can see the now chronology.
Post checks your video card.
So it checks the video card.
You will see information from the post on the screen. Post then checks to make sure you can find the CPU and that is communicating.
Then it will check the CPU. Okay, it will send signal to the CPU.
Then its test ran.
Then it will check the, it would check the random access memory. It would check the keyboard and mouse.
You might see the keyboard's lights flash. At this point, you would normally see an indication on the screen of how you
So a computer needs a bootstrap program to run when it's turned on. So basically the program has several tasks: to initialize the CPU registers, main memory, load the kernel and start the executing it. So the control goes to the instructions in the ROM, that is post instructions, power on self test instructions. So when this post instruction is executed, it would check the devices connected to the system such as CPU, RAM, etc., input and output devices. Once that initial post checkup is power on self test is successful, then what happens, the control goes to the boot sector or master boot record, MBR, or MBR is nothing but MBR is nothing but a special boot sector. Okay, so the control basically goes to the first sector in the hard disk, the first sector 0. Already we have discussed what is a sector, right? So cylinder 0, okay, then uh, then read write head number 0, then sector 0. So the very first sector in the hard disk is called boot sector. So in that boot sector there is a program called Bootstrap Loader. So the Bootstrap Loader, what it does, it will load the operating system kernel into the memory. So once the Bootstrap program loads the operating system into the memory, the operating system takes the control. Okay, so this is what I want to tell about the booting process. So I think I have covered all the points. In fact, the initial program is often very small, often just loads the bigger bootstrap program, and this block will be stored in the fixed location called the boot block. So this basically the boot sector, this is the boot sector, or we can say MBR, master boot record. It is in the hard disk, the very first sector in the hard disk. Once the read only memory finishes the power on self test, okay, it will transfer the control to the MBR, master boot record, or we can say the boot sector, so, or we can say boot block. So here there is a bootstrap program that will load the operating system into the memory. So next concept is called swap space management. The extension of the main memory in the hard disk is called swap space, or we can say the space in the hard disk which is used as an extension of the main memory. We can call it a swap space. The swap space can be implemented using a raw partition or using a file system. We have discussed when we installed the Linux operating system, Mint Linux operating system. While we installed the Linux, you saw how we created a partition for the swap space, raw partition. So why here the word raw partition is used? Because no file system is configured there. Okay, the partition is raw, it doesn't have any file system. So in some operating system we can implement the swap space as both as a raw partition as well as a file system. For example, just go to Linux, swap on -s. You can see this is a partition which we created while we installed the Linux operating system. The device is name is /dev/sda5. okay, so here there is no file system. Here we don't have any file system in place. So when we want a file system, okay, we have to execute this command. Okay, so this command sudo dd if equal, okay, this command, so it would create a swap space file of size 1 GB. So if you want more space, then you can increase the size here. Okay, so here this actually represents the size of the swap file. Okay, so you have to execute this command. This is the name of the swap file, and along with path, you have to specify the path where exactly you want to create the swap file, and then this is actually the size. If you want 5 GB, just multiply this with number 5. So whatever value you get, that you represent here. Then once the swap file, this is a file, once the swap file is created, we have to set the file permission 600. Then we have to declare the new file, swap file, as as a swap file. It belongs to a type called swap. So using this command sudo mkswap, using this command we just make this file as a belong to the swap file format. Then we will use this command sudo swap on space / swap file. By using this command we enable the swap file. So once the swap file is created, so we can see the command swap on -s. If you execute this command, you can see there is a swap partition here. This is the partition, and here the swap file. So in a single system, you can see both partition also available. Swap space is implemented as a partition as well as a file. So partition means, please understand, some space in the hard disk is used, and that some space, it doesn't have any file system. Whereas swap file means it's a single file. So it's a single file within a file system that is used as the swap space. And you can see the swap partition and swap file has some priority. So -1 means it has high priority, and swap file partition has high priority, swap file has a low priority. So by default the partition would be used since it has the high priority. Suppose you want to change the priority also, you can change the priority using some commands. You can change the priority. And also, suppose you don't want the partition, but you want the swap file, then you can disable the partition using the commands. You can disable, you can change the priority, so you can do a lot of manipulations. So this is what I want to discuss about the swap space management. So please understand the extension of main memory in the hard disk. Some space in the hard disk used as the extension of the main memory. So this can be implemented as a file system as well as a raw partition. In Windows operating system, there is only file system. There is no raw partition. But in the case of Linux, just now I showed you the example Mint. In Linux, we can implement both file system as well as a raw partition. And if you compare both, the raw partition is better in terms of speed because it doesn't have any file system when you compare the raw partition with the file system. So some operating system like Solaris, Linux, both file system and raw partition can be used. If you want when you have both, you have priority numbers. So based on the priority, we can select the default swap space management, whether we want a file system as the default one or the partition as the default one. We can decide based on priority. And also if we want to disable the partition, there is a provision to disable. Okay, but don't worry about the practical things. As far as the theory is concerned, please try to understand this concept. So just practical whatever I have showed you is just to enhance your knowledge. So don't worry about the commands and all. Okay, just try to focus here, try to understand the concept, what is swap space management. So with this I conclude the chapter 12 about the disk storage. Thank you very much.